Hi, thanks everyone for coming. Again, my name is Michael, and I manage the ML team at Stripe. So in case you haven't heard of it, this is not it. Oh, here we go. Stripe builds tools for online commerce. So what does that mean? Most basically, it means taking credit card payments online. And 5 years ago, it was surprisingly difficult to do this. If you were a startup, you had to go to your local bank, fill out some forms, write some terrible XML API calls, and so forth. But now you can do it with a simple RESTful API call to Stripe. But we're more than just credit card payments. For example, you can take payments in Bitcoin or in Alipay, which is popular in China, using our Stripe checkout form. And very recently, we launched Stripe Relay, which allows you to store product information directly with Stripe, which will then inject into social media streams, so your customers can buy directly from tweets, as in this example. So Stripe is a platform for commerce, and I want to talk to you about how ML has evolved there. And perhaps unsurprisingly, the canonical example of ML at a payments company is fraud detection. So I won't spend too much time on the subtleties of fraud, but I want to talk a bit about exactly how fraud happens and why it hurts the people who use Stripe. So let's say I say something here that gets me fired, and I have to start living a life of crime and of professional fraud. So what would I do? First, I would go online and buy dumps of credit cards. These are websites usually hosted in the deep web. And I can go there and I can buy, say, a dozen, 2 dozen, 3 dozen credit card numbers from between $5 to $20 each. So these dumps are usually acquired by breaches of retailers, for example, the Target breach from 2 years ago, or from hacks of online merchants. So I go there, I buy a bunch of cards. So what do I do next? I take those cards and I go to a retailer that sells expensive and popular items. So in this case, TVs. So I'll take each of those cards and I'll buy a TV from Best Buy for $1,800. Eventually, that TV will arrive at my door, and I'll go sell it on Craigslist or eBay at a discount, say for $1,000. So now I've pocketed $1,000 minus the $10 cost of the card that was stolen. So I'm happy. What happens next? A few weeks later, the cardholder will notice that there was a charge on his or her statement for $2,000, and it will dispute that charge with the card issuing bank, Wells Fargo, Amex, Chase, or whatever. So this is called a dispute or a chargeback. Now let's pretend that Best Buy uses Stripe. It doesn't, but for the purposes of this example, let's pretend that it does. So a cardholder tells American Express, hey, this is a fraudulent charge, I didn't make it. Amex tells Stripe, and then Stripe has to go to Best Buy and tell Best Buy, the cardholder says this was fraud. Can you provide evidence that it was not? For an online transaction, you almost can never provide compelling evidence. So what ends up happening is that Stripe goes in, takes out that $1,800 from Best Buy's account, and it also levies a small fee. So at the end of all of this, the fraudster has $1,000, the cardholder is made whole, but Best Buy is out a full TV and a small fee. So clearly, Stripe wants to eliminate this kind of activity as a service to its merchants. So how do we detect fraud with machine learning? You can imagine that every time a charge is made at Stripe, we have a number of objects that enter a charge stream, or a stream of objects. And the things of interest here fall into 2 categories. There are what you might call static features. So these are things you can read directly off the charge: the amount in US dollars, the country in which the card was issued, the IP address, whether the IP was an anonymous IP or a hosting provider, and so forth. Then there are features that are statements about the charge's position in that whole stream. So what you might call aggregate or contextual features. A basic example of this is just the number of charges made at Stripe with the same card in the past day. So we take the static features and the aggregate features, we feed them into a binary classifier. That classifier spits out a score, and based on that score, we either block the charge synchronously as part of the charging process, or we allow it. Okay? So I won't talk too much about the details of the modeling itself. What I want to talk about is the data infrastructure that makes these kinds of models possible. So first, there's a caveat here, which is I'm not going to tell you anything particularly insightful or any sort of best practices. I'm just going to tell you what we did and how it got increasingly less bad over time, though by no means am I trying to say that what we did is great. And then the bit of context that will be useful for you to have going in, there are two bits. One is that Stripe's production systems are predominantly written in Ruby, which is not really the best language for data science or large-scale data processing. Second, one of our production databases is Mongo, which itself has the same qualifications of not being the greatest for data science. So for the purposes of this talk, we'll just assume that all of Stripe's production systems are in Ruby and that Mongo has all the data that we need to do this modeling. So what was our first attempt? So we have a Ruby charge service, and this is the service whose HTTP endpoints users are hitting to make charges. Every time a charge is made, we create some objects in Mongo. So the two items in the top left corner here represent the core of our production functionality. So what's the first piece of data info we had? This actually predated my arrival 2.5 years ago. Every time a change is made to Mongo, there's an entry appended to the Mongo op log. So every insertion, deletion, mutation gets an entry to the op log. And we wrote a custom tailor that monitors this op log and makes the corresponding change to a Postgres database. So this database was built originally for analytics so that people in sales and business could do some reporting, so they could pull numbers easily. But we realized we need some data store that's amenable to analysis. Mongo isn't the one. So how can we use Postgres to help us for our machine learning needs? So what did we do? We said, let's just dump all the data in this Postgres database. And just to be clear, there are tables in Postgres that are exact analogs of the collections in Mongo. So every field in Mongo, in a Mongo collection, will correspond to a column in the corresponding Postgres database. But Postgres also has a bunch of what you might call denormalized tables. This tailor has logic that says things like, well, here comes a charge. This charge has a foreign key reference to a card object. Maybe the denormalized charge in Postgres should have data from both of these objects. So we have what you might call raw tables in Postgres, denormalized tables as well, and we dumped the denormalized table of charges to a CSV, literally. And I literally SCP'd that CSV from Postgres, the machine on AWS, to my laptop, and then I SCP'd it from my laptop to HDFS. What were our features there? Our static features were just the columns that were computed as part of this tailing process to populate the Postgres database. So I just had to hope that everything I wanted, IP address, anonymous IP, amount, were already all in the database. And then for the aggregate features, I wrote a simple scalding job that would chop up the CSV, sort of crawl it, and sort of compute these aggregates. So there's a scalding job, which is a wrapper for cascading, that ran on Hadoop. So in the end, I would then take those two things, join them, and build a model in Python using scikit-learn. So it was a very manual, very janky process. One thing I won't go into much detail into is once we had a model trained in scikit, we had a custom serialization format. So we serialized the model in Python. We would literally then SCP things again to another production system, the scoring service for scoring and production. Now, of course, the most interesting part here is how we actually do the scoring. And what I mean by that is how do we compute the features that we used in training for our production scoring? Because again, we got these features directly from Postgres or from the scalding job that ran on HDFS. And the answer is that we had to re-implement everything from scratch in Ruby. So we had Ruby logic that operated directly on the Mongo objects to compute things like the amount in US dollars and whether the IP address was anonymous IP and so forth. And we also had custom Ruby logic to run the same aggregations. And we used Redis as our store for keeping track of the running values. Again, think of things like number of times we've seen the card in the past day. So where are we with all of this? We want to compute static features and aggregate features, and we want to do so both in training and in production. So static features and training we obtained directly from Postgres. We mostly had to hope that the guy who wrote the tailor was sort of thinking of the right fields for these normalized tables. Sometimes we would do additional computation in Python, but that was really making things even more complicated. In production, we wrote separate Ruby code trying to ape that logic to compute the same features directly from the Mongo objects. For the aggregate features, we would run scalding jobs on the CSVs that we dumped from Postgres. And in production, again, we had separate Ruby code to compute these and store them in Redis. In terms of what was good about this approach, I don't really have to say much there, but it did get us models, and it actually got us good models in production very quickly. And we can sort of laugh about how bad it is. My team laughs about it all the time now. I actually am not sure we would go back and change anything about this, because this was the way or the mechanism that got us to automated ML-based fraud protection in production as fast as we could have. And that was really a pressing need 2.5 years ago. What's bad about this approach, we can go on for a long time, right? It was janky. Part of your production workflow should not involve an engineer SCPing things between his laptop and various AWS instances. We were limited in our features in terms of what we could express. For the dynamic features or the aggregate ones, we were constrained by what we could shoehorn into Redis. And that really meant sort of just windowed counts. How many times did this thing happen over the past few hours? Obviously, a huge problem was the fact that features were defined in multiple places. Features were defined in this tailor that sent things from the Mongo op log to Postgres. They were defined in scalding. They were also defined in Ruby in production. So if you wanted to know something like how was X computed, you might have to go look in 3 separate repositories to find that. So needless to say, this was an incredible maintenance burden. It was error-prone, just terrible. The last problem here is one that sort of affected Stripe in general. It's not just one about this particular architecture, which is that a lot of our data models are mutable. So for example, there's a charge object after I buy something, and let's say the merchant issues me a refund. This is not reflected by just the addition of a refund object that has a reference to the original charge. State on the charge itself is mutated. And why this is important and terrible will become clear when I talk about what we did next. So for the next iteration, we essentially ripped out all of the Postgres. For every collection we had in Mongo, say for charges, cards, and so forth, there was a definition somewhere, it was written in Ruby, to define what the document looked like. So we wrote a parser that would convert each of those Mongo document definitions into a thrift definition. So for a Mongo charge, there was a thrift charge. For a Mongo card, there was a thrift card, and so forth. And then every night, as part of, surprise, a cron job, we would snapshot the entire Mongo database and convert it to Parquet, a columnar format living on HDFS. So essentially, every night, we replicated the entire production Mongo database into Parquet, and then we had sort of all of Stripe's history living there in HDFS. And then we said, OK, now that we have Parquet, we can write both our static features and our aggregate features in scalding. So this has the benefit that now there was sort of one canonical place to produce features for training. We had a bunch of scalding jobs. There was a DAG for the dependencies. And in the end, this pipeline of scalding jobs spit out Parquet somewhere that had all of our features for training. And that was an improvement. But everything else about the system remained the same in this iteration. We still were serializing models to our custom format, copying them over to the Ruby scoring service. And most importantly, the Ruby scoring service was still replicating the logic in Ruby to compute all of these features. So what does this look like now? We have scalding from Parquet and HDFS for both static and aggregate features and training. And again, production is still distinct code bases for Ruby. This was still a decided advantage, though. There was much less manual work, less, again, SCPing. And features were defined now in just two places. They were either defined in scalding or in Ruby for production. So it's no longer the case that to find the definition of X, you might have to look in the oplog tailor, or in production Ruby, or in scalding, or in Python. Now there were just two instead of four possible locations. But what are the issues? The primary issue is so that features were defined in two places. And this often led to divergence in definitions. Little bugs not getting noticed, so the definition of account in training would be slightly different from a definition from account of production. And for a while, we didn't even have automated tooling to alert us of that fact. We just sort of noticed divergence and drift and sort of scoring errors over time. So that was definitely a big issue. We were still shoehorning aggregate features into Redis, which is our production store. Data is still immutable, and sort of most crazily, we were ETLing the entire history of Stripe into Parquet every single night. Right? Because events were not immutable, or because they were immutable, that means that we weren't incrementally updating our Parquet stores. We were just re-snapshotting everything with every daily cron job. OK, so what is, now where you'll think the third iteration is still crazy. So what are we doing now? And my team and Ori gave me feedback that this slide is incomprehensible, so apologies. So what's happening right now? We still have the Ruby charge service, but now this charge service is emitting a stream of immutable events, where these events are being computed and generated by code that is written in Ruby. Okay. Each of these events corresponds to what I've been calling static features. So if I want amount in USD, if I want is this an anonymous IP address, and so forth, I write the code to populate that field in Ruby. Now, what happens to that event stream? It goes to two places. One, it still goes to HDFS and is still stored as Parquet. But simultaneously, it goes to an online aggregation service. And that service is responsible for computing these dynamic features, like how many times did we see this card in the past day. And the important part here is what or where the logic for that aggregation is written. When we do training data generation for these dynamic features, and when we do the online computation for production, it is the exact same piece of Scala code now that's computing those values. And what we did here is we took Twitter's Hummingbird platform, which is a platform for streaming MapReduce, and we worked on and we developed on it. So now job writers just write a job once, and the platform is responsible for both online and offline execution. So to summarize, or just to give you the overall feel, the overall state here, there is no more writing of static features in Scala. All of the static features are written as part of the event generation logic in Ruby. Dynamic features are also written just once. They're written in Scala, and the platform executes them either an offline mode on the events stored on HDFS, or an online mode as it sees them as they get past the online aggregation service. So one thing about this aggregation service is that it's a Lambda architecture system. And what that means is that it combines both online and offline processing. So the kinds of questions I can ask the service are things of the form, I have a card number. Tell me how many times that card number has been charged in the past, let's say, week. And it answers that question by looking at both an offline store, which gives it historical data, and combining that number with its values from an online store. So what that means, for example, is that every time a charge comes in today, this service is incrementing the online store to say, OK, here's another charge I've seen with this card today. So it can sum up the value from the online and the offline stores to give me the answer that I want. But what's interesting is that at the end of the day, the same aggregation logic is going to run in offline mode and recompute all the values that were computed online today. So if, for example, an event is dropped between the charge service and the aggregation service because of traffic or load, there'll be some temporary errors in the data. because the packet was dropped, and we're not counting that as part of the system. But when the offline job runs tonight, it will go back in and correct those errors and compute the correct values based on what it has in HDFS. So where does this leave us? For static features, we just have events, fields in the events on HDFS. They're computed in event generation in Ruby. For production static features, we're using the exact same event generation code to compute amounts and IP addresses and so forth in production. So the feature generation code for static features is the same both in training and in prod. And then for aggregates, we're again operating on the same stream, identical thrift events. It just happens to be the case that in training, these events are serialized in Parquet on HDFS, and in production, these events are coming in over the wire. But in both cases, you're writing code once in Ruby for static features, and once in Scala for aggregate features. One advantage of the system as well is because we're using Summingbird and AlgeBird, we have far more features that we can express. Essentially, any aggregate that satisfies a monoidal composition law can now be used. And people who write jobs don't have to worry about how to sort of shoehorn various counts into Redis. The platform takes care of all of that. And lastly, data is now immutable. We're dealing only in immutable events now, and we don't care about what's happening in the underlying Mongo models. The main disadvantage here is the fact that, let's say I add a new feature. Maybe, is this Josh's credit card? If I want to backpopulate that feature and add it to all of my historical events, I still have to go right now and write a scalding job that goes and adds it to all the existing sort of thrift structures on HDFS. So there is still a possibility now that if I do want to have a feature historically, or a new feature, I have to write code both to generate it for new events in Ruby and code to backpopulate it for historical data. At least the benefit here, though, is that that backfill Scala code is short-lived. You only run it once, and then you toss it, and everything in the future is still just being done in Ruby. So just to summarize, these are all completely obvious / vacuous statements. But we really felt acutely how terrible it is when there's a divergence between your production and your data environments. And this great paper from Google talks a little bit about this. So if you're starting a new company and you got to choose the stack, as I just talked to Pete about, choose something other than Ruby and Mongo. Feature generation really should sort of share code between training and production, because otherwise you're going to define things incorrectly, you're going to have divergence, and your models will be scoring on things that are definitely wrong. And finally, immutability is incredibly important for both infra and for modeling. Like, you don't want your data structures to be changing under you. And that's it. Thanks.
Great. I gotta give you a hug after that. I think, according to the Slack back channel, I think a lot of people want to give you a hug. We all feel your pain. Do we have time maybe for one question? Is there a mic out there? I'm a little blinded by the light, so there you go.
So you went through about 3 different iterations, at least in slideware.
Yeah.
Really, it was probably 5. Which of those things that you did in a later iteration should you have done earlier? Like, what did you put off till the later version that you really wish you'd gotten rid of in version 2?
That's a great question. And last night I was thinking, it's fun to laugh about this now, but in retrospect, would we have done anything differently? I think it's the case that, iteration 1 almost had to happen the way it did. We came in, that Taylor existed, Postgres existed, we needed models. There wasn't really that much to do there. I think what probably we should have done is put more thought into iteration 2, and a lot of what happened in the 3rd iteration should have happened earlier. Like, we had to rewrite all of our feature gen logic 3 times essentially, and I feel like we didn't gain as much with the second iteration as we might have wanted to, and we could have conceivably just jumped to this one architecture where everything was behaving as we wanted. So it's not a great answer, but I think like one had to happen the way it did, but there was some sort of room for wiggling between 2 and 3, and moving to that Lambda architecture sooner could potentially have been worthwhile. Just to give you a sense of the timelines here, like iteration 1 took about 3 months, and then we were just working on the models, did not change infra for probably a half year after that. The transition to iteration 2 probably took 4 months. Again, and there was this period of just working on the models. And for iteration 3, from the time we decided to adopt the Lambda architecture to use Hummingbird to the time we were able to have it running was probably another 4.5 months. So really, if we just sort of sat down at the beginning of iteration 2 and said we want to do that, we probably could have done it in not too much longer. I just think it's easy to say in hindsight. In a year and a half ago, we were just talking about how terrible Postgres was, or at least for this workflow. We weren't sort of yet pulling our hair out in terms of how bad rewriting sort of features in 2 languages was. So I don't think we had the foresight at that point to have known that we wanted to get to iteration 3. So even though it's easy to say we should have done both at that time, retrospect, we sort of had no idea that that was where we were going.
Cool. Well, thanks. I think we got to jump to the next talk.
Thanks.
So.